Well, here we go, here we go. Tonight we're going to solve some more linear quadratic systems, but we're going to do it graphically. And I think you're going to find that this method's a little bit easier sometimes than the algebraic approach we took last night. So as these pictures indicate, we're going to get our parabolas graphed, we're going to get our lines graphed, we're going to identify the intersections, and the name of the game is that these intersections represent the solutions. So we'll be in good shape there. So here's the question. How many solutions, or aka how many intersections, should we expect? Let's see what we got here. How many solutions or intersections should we expect when you graph a line and a what simultaneously? This looks like a quadratic function to me, which is going to produce, when we graph it, it's going to produce a parabola. So if we graphed a line and a parabola simultaneously, how many intersections would you expect? Well, there's really three possible outcomes. There's the traditional one that we expect, where you would see two intersections, okay? So there'd be two solutions. Or, believe it or not, here's a fancy one. It is possible, and let's see if I could draw it at all. That's not as good as I wanted it to be. Let's see, where there's just, we'll call this one intersection, or there's one solution, and in that situation we'd say that the line is tangent to the parabola. And then there is the possibility that the line just never does intersect the parabola, and if there's zero intersections, we'd say that there's zero solutions. So those are the three possible outcomes. Okay, how about this? How many solutions or intersections should we expect if we graphed a line and a, what would you call this? Yeah, this looks like a circle to me. So what happens if we graph a line and a circle simultaneously? Very similar to what we just saw. You could have the classical two intersections or two solutions, or you might have the fancy one where maybe, let's see, there's just a point of tangents. We'll say that the line's tangent to the curve and there'd only be one solution. Or you could have the situation where they just never do intersect and there's zero solutions. Well, you might laugh at this next slide, because I'm going to talk about keys to graphing linear functions, and I'm going to tell you what. Here's what you're probably used to doing, and here's your first instinct: is you want to solve for y, is what you're probably thinking that you want to do. And there's nothing really wrong with that. And we'd get 3y equals negative 4x plus 12. And then you would divide each term by 3, and we'd end up with a slope of negative 4/3 and a y-intercept of 4. Do you remember that? That this number right here is your slope, and this number right here is your y-intercept. And I'm going to tell you what, if you're in love with doing that, then by golly, keep doing it. In worst case scenario, you could always plug this function into your calculator and let the calculator do the work and go, copy down your table of values and graph it that way. But what I want to do is I want to take just a couple of seconds to introduce you to a different idea that doesn't require solving for y, because sometimes these fractions right here can get kind of annoying and so forth. So I want to talk about a method that doesn't require solving for y. And let's go back to the original here, 4x plus 3y equals 12. And the first thing I want to do is I want to try to find the x-intercept, which means I'm going to substitute a 0 for x, okay? Or I'm sorry, I said that wrong, a 0 for y. And so I would get 4x plus 3 times 0 equals 12, which is 4x plus 0. Divide both sides by 4, and you get x equals, oh my gosh, I'm on a roll, x equals 3. And then you could switch it up and say, okay, after you find the x-intercept, let's go find the y-intercept. And this time I'm just going to substitute the 0 for x. And even though I'm kind of drawing this process out, this is a process that you could literally do in your head in just seconds. And let's see, 4 times 0 is 0, divide both sides by 3, and you get y equals 4. And then what's nice about that is, see, you only need 2 points to graph a line. So you're saying, here's my x-intercept right there, and here is my y-intercept up here. Bada bing, bada boom, you're done. And that's the key. When we're graphing a line, all you need is 2 points. Okay, let's talk about keys to graphing a quadratic function. And the number one thing I want you to do is to find the vertex. And I'm going to introduce you to a new little formula that's going to tell us where the vertex is located on a quadratic function. Sometimes instead of the vertex, sometimes we call it the turning point. And the formula says x equals negative b divided by 2a. Okay? And once you find the vertex, we're going to plug the quadratic into our calculator. We're going to go to the table of values, and we're going to pick 3 points to the left of the vertex and 3 points to the right of the vertex. And if you include the vertex itself, that's a grand total of 7 points that we're going to plot. Okay, so as a general rule of thumb, on the last slide I told you we only need 2 points to draw a line, but today I'm going to recommend 7 points to draw a quadratic. So let's practice using this new formula that we've got, and we can put a couple stars next to it so it stands out in our notebook so we can find it tomorrow when we need it. So let's say I had the function y equals 3x squared minus, say, 6x plus 7, all right? So here's what I'm thinking. I know that a is equal to 3, b is equal to negative 6, and I know that c is equal to 7. And my formula, again, was just negative b divided by 2a, which in this case is if I negate the negative 6 and then divide by 2 times 3, I'm going to get 6 divided by 6, or 1. So we could say that the vertex is located at x equals 1. Then when I go to my table of values, I'm going to pick, let's see, make a little more room here. If I know the vertex is at 1, I'm going to put the vertex in the middle of my table, and I'm going to pick 3 points to the left and 3 points to the right for a grand total of 7. Okay, as far as circles go, sometimes you're going to get lucky, and the circle is already going to be in what we call center radius form. So just by looking at the equation, you know that the center is going to be, let's see, in this case the center would be at positive h and positive k with a radius of r. But we're going to assume that it's not in center radius form, and so the name of the game here is completing the square. Complete the square. And we're going to have to do it twice, once to find the x-coordinate and once to find the y-coordinate of the center. So let's make up an example here. Let's say x squared plus y squared. And right there you know it's a circle because both the variables are getting squared. And then maybe we said plus 4x minus 10y equals 11 maybe. So here's what we're going to do. We're going to focus on the x's first and foremost. And I'm thinking x squared plus 4x, then plus a special number minus that same number. Now we'll do plus y squared minus 10y plus a special number minus a special number equals 11. Okay, now remember, take half of this number and then square it. Take half of this number and square it. And let's group these terms and let's group those terms. X plus 2 times the quantity x plus 2. Let's see, minus 4 plus the quantity y minus 5 times the quantity y minus 5. I think we're pretty darn good at this. I don't think we'll need too much practice. And then I'm going to combine these two terms together to make x plus 2 squared. Then I'm going to combine these two terms together to make the quantity y minus 5 squared. And then in the meantime, I'm going to add 4 to both sides. And then I'm also going to add 25 to both sides. And that gave me a 30 over here. So my center would be at negative 2 comma 5. And my radius is going to be the square root of 30, which isn't the nicest one to plot. But hopefully today ours will be a lot friendlier than that. Here's a really fun little question that's going to make us think a little bit, and it certainly is going to challenge us just a tad bit. So we've got a circle with a radius of 5, and then you got another circle with a radius of 3. So one's a little bigger than the other one. Now D is going to represent the distance between those two centers. And we want to know how many intersections there are going to be between these two circles for different values of D. So let's start off with this one. What if the distance between the two centers was 8 units? So what I'm going to do is, I already drew the first circle that had a radius of 5, and we're going to use the same circle for all of our examples. Now I'm going to try to draw the smaller circle that had a radius of 3. Now they said I had to be 8 units away. So what you could do is, starting at the center, you could go 8 units in any direction that you want. I'm going to go 8 units to the left just because that's where I have the most room. And I think it's going to put my center right there. Now remember, the smaller circle only has a radius of 3. So if I went 3 units in every direction, and I'm not real good at drawing circles, but that's about as good as I'm going to get, there would only be one solution in that case. We'd say that the two circles are, any guesses? We'd say they're tangent to each other. All right, let's see if I can break out another color here. Let's see if we could do one where the distance was 10 units apart. Again, same idea. I could count 10 units in any direction. I'm probably going to go 10 units to the left just because that's where I have the most room. And I'm going to go 10 units would put me right there. Again, my center, or my radius, is going to be 3 units. Draw the best circle you can. And in this case, it's impossible, if those centers are 10 units apart, it's impossible for them to intersect. So we'd say there's going to be 0 solutions. What other fun colors we got here? Let's try blue maybe. What if the distances were just 1 unit apart? Again, you could go in any direction. I'm going to go 1 unit to the right of the original one. And if I did a radius of 3 units, how many intersections are possible? Well, this time, again, I'm going to say there's 0 solutions just because it's impossible for that smaller circle to reach the bigger circle. Let's see. What if we said the distance from the centers was only 2 units? All right, start with the purple. You can go 2 units in any direction you want. Just to prove you can do any direction, I'm going to go 2 units up from the purple center. And then I'm going to go radius of 3. And it looks like they just intersect one time right there at the top. So I'm going to say 1 solution. And then last but not least, what if the distance between the centers was 4 units? So let's try, I'm going to start with purple. And again, just to prove that you can go in any direction, I'm going to go down 4 units. And then, let's see. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And look at that. For the first time, we had 2 intersections, therefore 2 solutions. Okay, it is finally time to dive in and solve one of these systems of equations. And first of all, I've got a linear function here that's going to make a straight line. So for me personally, I'm just going to try to find the x-intercept and the y-intercept and then connect those 2 dots. If you're the other way around and you want to solve for y and do slope-intercept form, and by golly, knock your socks off, I'm going to find a y-intercept by substituting a 0 for x, divide both sides by -1, y equals -3, or I could say I'm going to find the y-intercept, or I'm sorry, the x-intercept by substituting a 0 for y, and x equals +3. And again, I'm just going to connect those 2 dots the best I can. In the meantime, I need to, let's see, what shape do I have over here? It looks like I got a circle over here, and I need to complete the square. So I'm thinking x squared minus 4x, create some spaces, plus y squared plus 6y, create some spaces, if I can squeeze them in there, equals -9. What's going in those magical spaces? Looks like I'm going to do +4 minus 4. I'm going to do +9 minus 9. And I'm going to focus on grouping them right here and right here. Let's see. I'm going to get x minus 2 quantity squared plus y plus 3 quantity squared. And I'm going to add 9 to both sides, and I'm going to add a 4 to both sides, and I think I just end up with a 4. So I've got a center at 2, -3. I've got a radius of radical 4, which turns out to simply be a 2. Okay, first things first, I'm going to take care of my linear function. I had a y-intercept of -3, I had an x-intercept of +3, and with a straight edge, let's see, I'm going to try to connect these points as carefully as I can, right? Okay, now the circle, let's see, 2, -3, looks like it's right there, and the radius is 2 in every direction, bada bing, bada boom, bada bing, and it looks like we're getting 2 really nice intersection points. If I wanted to identify them, the first intersection point is at 0, -3, and the second one is at 2, -1. And by golly, it's really easy to check those by just substituting them into the original two functions. Okay, last one for the night. I've got another line just like I had in the last example, but then we've got a parabola to work with instead of a circle. I'm not sure which one you like better. It's probably a toss-up. But as far as my line goes, if I substitute a 0 for x, I get a y-intercept of 2. And then if I substitute a 0 for y, check that out, I got an x-intercept of 2. It doesn't get any easier than that. Now as far as the parabola goes, let's find the vertex first. Do you remember the formula, negative b divided by 2a? So let's negate negative 4 and then divide by 2 times 1 to get, looks like 4 over 2 is 2. So I'm going to create this gigantic table of values, and where 2 goes in the middle, and I'm going to try to pick 3 points to the left and then 3 more points to the right. But I'm going to rely on my calculator at this point. I'm just going to type this function into y equals, and I'm going to use that table of values and fill them all in. Right now my calculator is giving me a 9, let's see, a 4, a 1, a 0, a 1, a 4, and a 9. And I'm going to try to plot everything the best that I can here. Let's see what we got shaking and baking. Let's see if I can enlarge this graph at all. Now as far as my linear function goes, I think I had a y-intercept of 2 and an x-intercept of 2. And again, I'm going to try to encourage you to use straight edges tomorrow. And we'll make it as long as we can and as straight as we can. We're going to be really super precise. And then I'm just going to start graphing this parabola the best I can. -1, 9, 0, 4, 1, 1. That looks like an intersection right there. Let's see. 2, 0. That looks like an intersection right there. Then we got 3, 1, 4, 4, 5, 9. And we'll draw the best looking parabola that anybody's ever seen in the history of math. And something like that. Alright, I'm going to bust out my red pen here. I've got the first intersections at 1, 1, the second intersection right there at 2, 0, and those are the two solutions. Remember we said there could be 2, there might be 1, there might be 0, and in this case we've proven 2. Again, real easy to check by just substituting these into the original function. So not a bad night at all. A couple of new things to throw at you, a couple of new things that we could try. We'll step out of our comfort zone a little bit tomorrow. So good luck, and we'll catch you later.